Hello, and welcome to this presentation, Understanding EMC Precompliance. In this presentation, we'll provide a short technical overview of EMC precompliance, how precompliance testing is performed, and the most common instruments and accessories used in EMC precompliance testing. Before we talk about precompliance, we first need to discuss what we mean by compliance. Regardless of their intended purpose or function, modern electronic devices must meet two requirements. The first of these is that they should not emit undesired radio frequency signals, since these signals could then cause interference to other nearby devices and/or spectrum. This is commonly referred to as EMI, or electromagnetic interference. The other requirement is that the device itself be relatively immune from, or not adversely affected by, radio frequency signals. This is called EMS, or electromagnetic susceptibility. With regard to EMI, devices must be tested to show that they comply to standards, such as CISPR or MIL standard, specified by the responsible regulatory agency, such as CE or FCC. This testing must be done before selling, or even marketing, a product. There are literally hundreds of different EMC-related standards, and these differ based on things such as country or region and the expected use. A device intended for the home usually will have different requirements than one intended for industrial or military applications. It's very important to remember that EMC testing is largely about testing for compliance to various standards. Compliance testing can be divided into two main categories. In conducted testing, we measure signals that the EUT, or equipment under test, introduces onto the AC power or mains network, most often through its power cord. Because we're looking at conducted signals, the measured frequency range is relatively low, usually 9 kHz to 30 MHz. In order to measure these conducted signals, the EUT is normally plugged into a special device called a LISN, which is then connected to our measuring instrument. We'll go into more detail on this later in the presentation. The other type of testing is radiated testing, in which we measure the signals radiated by the device under test. Radiated testing is usually tested from 30 MHz to 1 GHz, although some standards may require testing at much higher frequencies. Since these are radiated tests, an antenna is required, which is then connected to our measuring instrument. Note that for radiated compliance testing, a shielded chamber or suitable open-air test site is also required. In the case of both conducted and radiated emissions, compliance testing is almost always done by a certified third-party test lab or test house, not by the manufacturers themselves. These compliance test labs follow strict and precise procedures defined in the standards, and this in turn requires specialized equipment, special facilities such as chambers, as well as trained testing personnel. As you might imagine, compliance testing can be very expensive, usually costing thousands or tens of thousands of US dollars per attempt. Unfortunately, failing compliance testing is not uncommon. Depending on the type of testing and the standards involved, the failure rate is often in the range of 70 to 90%. If any portion of the test has failed, the manufacturer must schedule a new test, which includes paying the testing fee again as well. Any product redesign or remediation, of course, also requires additional time and money before retesting is possible. One universal truth when it comes to EMC testing is that problems can be fixed more easily, more cheaply, and more quickly when they're discovered earlier in the design cycle. Pre-compliance testing, on the other hand, is testing done by the device manufacturers in their own labs before compliance testing, and this is intended to increase the probability of passing the official compliance tests. As mentioned a moment ago, significant time and money can be saved if EMC-related issues are caught and corrected early in the design cycle. Formal compliance testing is essentially pass-fail, and does not provide much insight into the causes for the failure. Pre-compliance testing, on the other hand, can be stopped at any time, and the reasons for issues can be thoroughly tested and debugged when necessary. And although pre-compliance testing rarely is exactly identical to compliance testing in terms of instruments, tools, and techniques, The goal should always be to duplicate compliance tests whenever possible or practical. Let's take a graphical look at the design to compliance process. As already discussed, it's a good idea to incorporate EMI debugging and analysis into the design process itself. If initial measurements don't reveal any serious issues, the next step is to move into pre-compliance testing. Here, the attempt is to test the EUT in a way that most closely approximates the required compliance tests. If any of these tests are failed, the EUT is debugged and any necessary changes are made. Once pre-compliance tests have been successfully passed, the next step is full compliance testing at a lab or test house. If all goes well, this testing will result in formal certification, allowing the device to be marketed and sold. Otherwise, the device moves back into pre-compliance testing and/or debugging to resolve any outstanding issues. Remember that the goal of pre-compliance testing is to minimize the time and cost needed to successfully complete compliance testing. So what do we need in order to perform pre-compliance testing? There are two general requirements. The first is deciding where the pre-compliance tests will be performed, in a chamber, indoors, or even outdoors. The second is choosing the instruments and accessories used to perform these tests. In the remainder of this presentation, we'll cover each of these topics in detail and explain any differences between compliance testing and pre-compliance testing. Let's start by looking at the test location or site. Compliance testing normally requires specific test environments or test setups. In the case of conducted testing, the testing environment is relatively easy to set up. Usually, all that's needed is a simple ground plane and a non-conductive table, in addition to the test instruments and accessories. Therefore, it's not difficult to perform conducted pre-compliance testing almost identically to how full compliance testing is performed. Radiated compliance testing, on the other hand, generally requires a shielded chamber or suitable open-air test site. Due to the size, cost, and complexity of configuring these facilities, most radiated pre-compliance testing cannot precisely duplicate the compliance testing environment. As a result, modifications are often made for radiated pre-compliance tests, such as adding margins to the results. For example, if a smaller test chamber is used, measured emissions will be stronger because the antenna and the equipment under test are closer together, and thus any emission limits will need to be raised. Going from a typical compliance distance of 10 meters to a typical pre-compliance distance of 3 meters, as shown in the picture here, often requires raising the emission limits by about 10 dB. Next, we'll look at the two main categories of instruments used in pre-compliance testing. Spectrum analyzers and/or EMI receivers are most commonly used to measure emission limits, whereas oscilloscopes are primarily used for debug and/or troubleshooting. Let's start by looking more closely at spectrum analyzers and EMI receivers. Both EMI receivers and spectrum analyzers are frequency domain instruments. That is, they measure and display power as a function of frequency. Recall that EMI testing involves measuring conducted or radiated power levels over a range of frequencies defined by a standard. Passing an EMI test, therefore, means having these values fall below a defined limit line, something we'll talk about in a few slides. Although it's possible to make these kind of measurements by hand, spectrum analyzers and EMI receivers often have a special automated routine that steps through or scans the frequency range of interest. This functionality may be built into the instrument itself and/or controlled via external software. Some EMI testing features can be found on both instruments, such as limit lines or spectrograms. Other features are only found on EMI receivers. Two important functions that are only available on EMI receivers are time domain scanning and preselection. Before we go on, let's spend a few moments discussing some of these features and how they're used in both compliance and pre-compliance testing. Limit lines are a basic but vitally important feature on both EMI receivers and spectrum analyzers. Recall that compliance testing involves checking power levels at different frequencies in order to determine whether the conducted or radiated levels are below the specified limits. These maximum power values or limits are commonly defined in terms of standard-specific limit lines, which can either be configured on and/or loaded into our measuring instrument. For example, this limit line is first loaded into our spectrum analyzer or EMI receiver, and then measurements are made. A fail result occurs whenever the measured power crosses the limit line. As we'll discuss on the next slide, measurements of power versus frequency are often made with different detector types, such as peak, quasi-peak, and average. And in this case, limit lines are defined for the specific detector type used. In this example, the peak limit line was violated by the blue peak detector trace, but the quasi-peak limit line was not violated by the green quasi-peak detector trace. It might be helpful to pause for a moment to explain these different detector types and their role in compliance and pre-compliance testing. Detectors determine how multiple measurements made during a time interval are combined into a single value. For example, if the measured signal is pulsing over time, and we calculate results over these intervals, the resulting values will depend on the detector type. For the peak detector, the maximum value is chosen. The quasi-peak detector, on the other hand, measures the annoyance of a signal using a type of charging and discharging behavior. And the average detector simply yields the average value over each interval. Compliance measurements often use the quasi-peak detector, but in pre-compliance, the peak detector is more common. There are two main reasons for this. First, the peak detector is always much faster than the quasi-peak, usually by at least several orders of magnitude. Additionally, the peak detector results are always higher than quasi-peak, meaning that if the test passes pre-compliance testing using the peak detector, it will also pass using the slower quasi-peak detector. Another common feature used in EMI pre-compliance testing is spectrograms. A spectrogram is basically a plot of power versus frequency versus time. In order to display these three quantities in only two dimensions, signal power or intensity is mapped to color, red usually indicating higher power, and purple or violet indicating lower power. Spectrograms are sometimes referred to as waterfall diagrams because they're drawn from top to bottom. The most recent measurements appear at the top line of the display and then flow downwards. Spectrograms are useful in that they allow easy visualization of how signals change over time and over a range of frequencies. This enables easy identification of time-varying behavior, such as drifting, frequency hopping, etc. Spectrograms also make it easier to see smaller signals in the presence of larger signals. Most spectrum analyzers and EMI receivers have spectrograms as a standard feature, and spectrograms are also common on oscilloscopes when displaying frequency domain information in so-called FFT mode, something we'll cover in just a few slides. The next topic is preselection. Earlier, we mentioned that preselection was an important differentiator between EMI receivers and spectrum analyzers. In EMI testing, the input signal is neither known nor controllable. Therefore, it's possible that out-of-band or off-screen signals could overload the first mixer in our measuring instrument and cause compression or distortion, leading to invalid or misleading measurement results. Preselection is a method used in EMI receivers to protect the first mixer. Preselection is normally implemented as a bank of filters that allows the receiver to select only the frequencies of interest. The particular filter is chosen automatically by the receiver based on the configured input frequency. For example, if the input frequency were 30 MHz, this filter would be used. When the input frequency changes, such as during a scan, a different filter would be used. Many EMI standards require the measuring instrument to have preselection, and this is why compliance testing is performed using EMI receivers rather than spectrum analyzers. Although many spectrum analyzers do have something called preselection, this is usually just high-pass filtering using YIG technology, rather than the switchable filter bank form of preselection that we've discussed here. Another feature only found on EMI receivers is something called time domain scan. Traditionally, EMI receivers made measurements using a step frequency scan with a small resolution bandwidth. This method of measuring is very accurate, but it can also be very slow, especially for the wide spectral ranges found in radiated measurements. Newer EMI receivers are able to overcome this limitation by using time domain scan, in which the measurement range is split into very large blocks of spectrum, each of which is then digitized and processed using the fast Fourier transform. Time domain scan provides a very significant speed improvement over the traditional step scan, and it accomplishes this without losing measurement accuracy. Time domain scan has been approved for most types of compliance testing, and therefore it's often also used to speed up pre-compliance testing as well. Now that we've covered the use of receivers and spectrum analyzers, we'll move on to discuss oscilloscopes. Compliance testing is normally done with receivers, but scopes are very common in pre-compliance testing. Unlike a spectrum analyzer or EMI receiver, oscilloscopes are primarily used to look at time domain information, that is, voltage as a function of time, and are thus a vital tool in electrical and electronic design. This makes scopes very valuable when trying to locate and debug, or remediate, sources of non-complying emissions. Many modern scopes do, however, also have the ability to make frequency domain measurements, and we'll talk about this in more detail on the next slide. An additional benefit of scopes is that many modern scopes have a relatively wide bandwidth. Like EMI receivers and spec-ans, scopes can be used to look at both conducted and radiated signals, and in the case of radiated signals, this is often done using so-called near-field probes, another topic we'll come back to shortly. One drawback of using oscilloscopes for pre-compliance testing is they usually don't natively support the limit lines that we looked at earlier in this presentation, although limit lines and other EMI-related features can sometimes be implemented using an external software program that obtains and processes data from the oscilloscope. Oscilloscopes display frequency domain information by performing a fast Fourier transform on the acquired time domain data. The result is similar to what's seen on a spectrum analyzer or EMI receiver, that is, a display of power versus frequency. One important advantage of using an oscilloscope for pre-compliance testing is that some scopes allow the time and frequency domains to be viewed simultaneously. This in turn allows events in one domain to be correlated with events in another domain, and this is extremely helpful when debugging EMI issues. For example, instead of the traditional time domain trigger found in oscilloscopes, a frequency domain trigger is often also supported. This trigger occurs when a frequency mask or region, shown here in green, is violated. Once the scope has been triggered by this frequency domain event, the related or underlying time domain event can then be analyzed to determine the root cause of the violation. Before moving on, let's briefly summarize the instruments used for pre-compliance testing. EMI receivers are unlike both spectrum analyzers and oscilloscopes in that they support both preselection as well as time domain scan. Other common features such as spectrograms and limit lines are generally supported by all three instruments, although external software is normally required for limit line testing using an oscilloscope. It's important to keep in mind that EMI receivers tend to be specialized instruments compared to the more general-purpose spectrum analyzers and oscilloscopes. However, EMI receivers are also the instruments used for full compliance testing, so using them for pre-compliance leads to closer correlation with compliance testing results. And lastly, wide bandwidth and the ability to correlate time and frequency domain data makes oscilloscopes very valuable for debugging issues discovered during pre-compliance testing. In addition to the different types of instruments that can be used for pre-compliance, there are a number of different tools or accessories that are commonly used when making pre-compliance measurements. These are LISNs, different types of antennas, near-field probes, and software. We'll close out this presentation by spending a few minutes discussing each of these and the role they play in pre-compliance testing. As mentioned earlier in this presentation, a LISN, or line impedance stabilization network, is used in conducted emissions testing. You may also sometimes hear these referred to as artificial mains networks or V networks. As the name implies, one of the main functions of a LISN is to provide a stable impedance on the AC mains end of the EUT's power cord. This helps ensure consistent, repeatable results regardless of where the test is conducted. Another important function of a LISN is that it blocks any RF signals present on the AC mains from entering the EUT via the EUT's power cord. This helps to ensure that any measured emissions are coming from the EUT, rather than being conducted in from the AC mains network. LISNs are very easy to use. The EUT is plugged into one port of the LISN, and the measurement port is plugged into our measuring instrument. LISNs are used in both compliance and pre-compliance testing, so conducted pre-compliance results made using LISNs are often a very good predictor of compliance measurement results. Radiated compliance testing, on the other hand, requires antennas to measure the signals emitted by the equipment under test. Note that radiated compliance testing is always done in the so-called far field, with the antenna typically being placed several meters or more from the EUT. Because of the wide frequency ranges required by most radiated testing standards, typically a gigahertz or more, broadband antennas, or a combination of antennas, are often needed to efficiently cover the entire frequency range. Some common examples of these types of antennas are log periodic antennas or biconical antennas, such as the one shown on the right. Well-designed and properly configured antennas allow for very precise measurements as well as frequency compensation using so-called antenna factors. The same type of antennas can be used in both compliance and pre-compliance, but as mentioned earlier, the distances between the antenna and EUT are often shorter in pre-compliance testing, and this in turn requires some modifications to the radiated limit lines. With regard to troubleshooting or debugging the causes of emissions, these types of antennas are, however, not very appropriate. They're normally too large and too bulky to provide precise information about which part of the EUT is generating emissions. As the name implies, near-field probes work in the near field, that is, in close physical proximity to the source of an emission. Although there are various definitions of near field, as a practical matter, near field in EMI debugging is usually on the order of a few centimeters. Because of their small size and their proximity to the source, near-field probes have high spatial resolution. That is, they can often be used to very precisely locate the physical source of an emission, even down to a pin on a chip or a trace on a printed circuit board. Clearly, this is very helpful in EMI debugging, as it provides information on where an offending signal is coming from. On the other hand, near-field probes only support relative measurements. That is, they're good for finding sources of emissions, but cannot be used to make practical or accurate level measurements for the purposes of verifying limits. Near-field probes can be divided into two main types. H-field probes react to the magnetic field and often have a loop-type shape. E-field probes, on the other hand, react to the electrical field. In most cases, commercial near-field probes come as a kit that contains both types of probes. One final note, the signals picked up by near-field probes can be quite small, so unless they're connected to a low-noise instrument, a preamplifier may be needed. Software is another very common component in pre-compliance testing, and it has two main functions. The first of these is scripting or automating tests, whereby the program communicates or controls multiple instruments and accessories through a single interface. The other important function of software is collecting and displaying the measured data. Compared to the individual instruments, pre-compliance software packages can provide a more sophisticated display with advanced customization options, such as special limit lines. A software package can also easily incorporate antenna factors, cable loss, etc. into the measurement results. And the ability to generate custom reports or export data is a standard feature on most pre-compliance software packages. Finally, software provides higher speed and better repeatability than manual operation, allowing rapid and accurate pre-compliance testing to be performed even by people who are relatively new to pre-compliance testing. Let's end with a brief summary. Most electrical and electronic devices must be tested by third-party labs to ensure that they comply to various conducted and radiated emission standards. The failure rate in these tests is often quite high, and the required redesign and retest can require significant time and money. Pre-compliance testing is in-house testing done before the compliance test and is intended to identify problems early in the product cycle, where these issues are faster and cheaper to correct. Properly performed pre-compliance testing, therefore, increases the chances of passing the full compliance tests. The primary tools used in pre-compliance testing are EMI receivers, spectrum analyzers, and oscilloscopes. Generally speaking, receivers and spectrum analyzers are used for making measurements of emissions, and oscilloscopes are used to locate, identify, and debug the sources or causes of offending emissions. In addition to these instruments, common accessories used in pre-compliance testing include LISNs, antennas, near-field probes, and special software packages. This concludes our presentation, Understanding EMC Pre-Compliance. If you'd like to learn more about EMC testing, pre-compliance, or solutions for pre-compliance testing, please see the links in the video description. Thanks for watching.